differential equations, and this is 5.6 we're talking about here. Differential equations. We're going to focus on some application stuff, growth and decay. For today, we're going to make sure we understand how to do some new things with differential equations first. So in the past, we've done differential equations. A differential equation is something like this: dy dx equals x squared plus 2. That's a differential equation because it's an equation that's been differentiated. We took the derivative of y with respect to x. But usually when we look at these, our question is, what was y equal to? Like, that's usually what we do on these. We figure out, well, if the derivative is x squared plus 2, what's the original? So we kind of have to undifferentiate it, or take the antiderivative, which is just a fancy way of saying, hey, let's integrate this thing, right? So we've done a few of these in the past where we just said, all right, let's go in and now integrate both sides of this. So we integrate both sides of, all right, well, actually, before we do that, we do a little rearranging here. We say, all right, dy equals x squared plus 2 dx. Technically, that's what we would normally do. Now we integrate both sides and figure it out. Because what is the integral of dy? Remember, this is 1 dy. The integral of the derivative of y is just y. So that's where we get our y from. And then we just integrate the other side and we say, okay, this is going to be x cubed over 3 plus 2x plus some c. So that's what we've done up till now. But that's only when the equations are written nicely like this one. If we have a differential equation where it's like, all right, we got our y on the left-hand side, we got our x squared plus 2 on the right-hand side, we got all our x's on one side, all our y's on the other side. This is easy, piece of cake. But sometimes it's not always written so nicely. So, so our question is, what if there are more variables? So we could say, really, it's what if there are variables on both sides? So, and by variables, I mean, what if we have x and y on both sides of the equation mixed up on both sides and mixed up together? So, question is, what are we going to do if we have something, for example, that looks like this? Y prime, or dy dx, equals the square root of x over 3y, let's say. So this is a little bit different because they've got this 3y there. A little bit more action going on here. So easiest way to do this is just start by rewriting this. I'm going to actually change our y prime here. I'm going to change that to dy dx. It'll make our problem a little bit easier. And you can see why we can't just take the integral of both sides at this point. Because for starters, I mean, I've got a y on this side along with the x. And it's like, okay, what are we going to do with that? So we have a new method we can do here. So first thing we do is a little rewrite. I'm going to rewrite this, and I'm going to say that this is dy dx equals square root of x over 3y. So just get they call it the Leibniz notation for this one by Friedrich Leibniz. He's the one who came up with it. I don't know if that's his first name, but it sounds right. And then I'm going to rearrange this thing a little bit. I'm going to put all of the y's on one side and all the x's on the other side. So I'm going to take this 3y and multiply both sides by it. So I'll have a 3y dy on the left side, and on the right side, it's going to be the square root of x, which I'm going to write as x to the 1/2 from here on out, dx. But now you can kind of see what we're about to do here, because I'm about to, if I integrate both sides now, I can integrate with respect to y on the right, or on the left, and integrate with respect to x on the right. So now I'm just going to do that step there. I'm going to integrate both sides and say, okay, we've got the integral of 3y dy on this side equals the integral of x to the 1/2 dx on the right. So I'm just ready to do each integral individually. So left-hand side, that's pretty straightforward, right? Bump up the values, this is just power rule, right? Bump up the exponent 1 and divide by it. So this would be 3/2 y squared over here. And on the right-hand side, so I'll do a little quick trick here, because we added 1 to 1/2, that's 3/2, right? And we're going to divide by 3/2, which is the same as multiplying by 2/3. So I'm just going to skip right to that step there. So it'll be 2/3 times x to the 3/2 power. So we divided by 3/2 and it turned into 2/3. But of course, we're doing integration here. This is not a definite integral. So I do need a plus c on this at the end. But this isn't done yet. What I really want to do here is kind of rearrange this and clean it up a little bit for our purposes. So I'm going to take that x over to the other side with the y squared. And I'm going to write this as 3/2 y squared minus 2/3 x to the 3/2 equals c. Okay, so far so good. Let me bring this back to center here. And just to get rid of the fraction, and remember, c is a constant, unknown constant. We don't know what it is. So if I was to multiply c by like 6, it'd still be a constant c that we don't know yet. So I'm just going to go through and I'm going to multiply everything by 6. Anybody know why I'm using 6? Common denominator, right? Over here. Multiply by 6, I can get rid of these two fractions here. And this will turn into, if I multiply everything by 6, multiply this by 6, it'll be 6c, and this will just be, well, this 6 divided by 2 is 3 times 3 on top. It would be 9y squared. This cancels out and makes 2, so it'd be minus 4x to 3/2. Now, instead of just saying 6 times c, let's say this was like a c1 earlier here. What if we let our c equal 6 times c1? Whoops, that's a c. That's something else. That way I can just rewrite this and say we have a c over here, a constant, 9y squared minus 4x to the 3/2, and that's it. Solved a differential equation that was not in the nicest form we had before. So yeah, that's what we're doing here. We're solving the differential equation, is what, just a differential equation, just to be clear on our instructions for something like this and what we're actually doing, solving a differential equation. Now this is actually graphable. You can plug this into Desmos and like try some different constants out of it. And this would be the graph. It's actually like half of a hyperbola, which you guys should have done back in pre-calc at some point. And one other thing too, remember with some of these types of problems, we might have been given a point at the beginning and said, oh, this thing passes through the point like 0.5 or something like that. Come up with a particular solution for this. So remember, we're just taking the 0 and the 5 and plugged it into our x and y and gotten a c value out of it. And then we could get an actual like finished equation where the c is some known point based on what it passes through. Because otherwise we kind of have that like slope field situation where we kind of know what it'll look like at certain points, but we don't know exactly where it goes through. So far so good with this? Just to recap what we did up here, make it nice and big. We took this, and once we rewrote it and looked at it as dy dx, we just rewrote it so that we had y's on one side, x's on the other side, then integrated. That was our key step after that. So maybe let's just take one problem here. What do we got? 3 minutes only? I might have to do this separately and something later on. But this is what a problem we'll look at later. This is actually number 20 from your book, which is find some function f of t passing through the point 0, 10 if dy dt equals 3/4 y. This is kind of an interesting little problem, but you kind of work it the same way, where you say, okay, get all your y's on one side, get your t's on the other side. So you could rewrite this and say, well, this is the same as, well, I got to divide both sides by y, so it would be 1 over y dy equals 3/4 dt. And you integrate both sides. Now, this is something we've done before, integrating 1 over y. Hopefully this one, anybody remember? Whoops, I keep doing that. I don't want to scribble it out. 1 over y, taking the integration of that. Anybody remember what that is?
ln.
Yeah.
Log of
Yeah.
y.
Yeah, it's just natural log of y, ln y. So that's an easy one. And the other side's actually pretty easy too, right? Because this is, you know, it's the same as if I said, oh, take the integration of dt, just add the t, right? So if you integrate both sides at this point, you just end up with ln of y equals 3/4 t plus some c. Now, where you go from there is kind of interesting, because technically, I've probably, if I wanted to put this in terms of t and y, because it's saying find an f of t, all right? So really it's saying our f of t in this particular case is y. I got to get y by itself. But how do I change a natural log of y into just y? What would I have to do to both sides?
Both sides.
Both sides, or e raised to the power of both sides. Because remember, e to the natural log of x is just equal to x. So if I said e to this and e to all this, well, the left side would just turn into y, but now you got to do some fun stuff with it. This guy here, the dy dt of 3y, or 3/4 y. So we did a little separation of variables with this one. We rewrote it with 1 over y dy and 3/4 dt. So then we did the integral of both sides, which gave us this. Integral on the left was pretty easy, and then on the right side, it's just 3/4 t plus c1. The part we didn't get to yesterday was, what do we do after we raise to the e power of both sides? So take both sides and raise both sides to that e power. It's one way to think about it. So we ended up with this setup right here. And the interesting thing about this is I can use a little exponent law right here to in reverse to change this e to the 3/4 t plus c1 to two separate e's, e to the 3/4 t times e to the c1. But think about it like this: if I'm raising e to some constant, well, it's just still a constant, right? E is a number, it's not a variable. C is a number, it's not a variable. So let's just call that C. So we took that and said, all right, this is just C. Let's write that out front. So our kind of general format here was this one. And like we've done before, if I want the particular solution, remember we were given that point 0, 10 up front. So we just plug that in for our t and our y. Solve for c. C was equal to 10. So our final equation was this one over here. So that was kind of the idea behind it. Okay. So it was just kind of a little interesting step right here, using that separation, using that exponent law, which is kind of important for us. And we'll come across that again today. Let me erase all these. I want to get rid of all these things, so when you look back at that later, you don't see all those extra marks. So we're gonna kind of take another problem here, or another concept. So a little bit of a notes introduction at the beginning here. So this is, we're going to be focusing on growth. Let me make that a little bit thicker. Growth and decay. So this is kind of interesting where these formulas come from, because you've probably seen these formulas back in pre-calculus at some point. You just didn't know where they came from. So we're actually going to derive where these came from back in the day. So here's the thing to keep in mind with this. It's oftentimes that the value of a variable is often proportional to the rate of change of that variable. So in other words, as the variable, say, increases, the rate of change also increases at a proportional amount. Or as a variable decreases, the rate of change also decreases at a proportional amount. So they kind of go lockstep with each other. And you kind of think about it, that's like, oh, that kind of sounds like an exponential thing, right? Just stopping and think about it. It's like, oh, exponential increases as you go over time. You know, if something increases exponentially, well, the rate of increase, you know, you see those curves, you've been seeing a lot of them on TV, I'm sure, with all this, you know, this stuff with the corona, where the increase goes, it keeps going up and up and up, where the slope increases as those values increase. So this is something like we're actually pretty familiar with right now. So you can think about it like this. We could say that the rate of some variable, dy, let's say over time, okay? So rate of change, so it's change of a variable over time. This is our rate of change here. We're saying it's proportional, there's our is with the equal sign, is proportional to the variable itself. So here's the variable itself. So this is the rate of change of the variable, and then the variable itself. But then we have some proportionality constant in there too, okay? So this is a proportionality constant that we would use to figure out what that rate of change actually is. You know, there's some constant in there when we have proportions. We don't just say, hey, the rate equals y. No, we say the rate equals y, but you know, some constant in there that is a multiple of that, or sometimes it decreases, so it could be less than 0 too, or less than, well, in this case, less than 1. So what we're going to do though is, you know, this might kind of look familiar to you. It's similar to what we've done with some of these problems already. What if we take that, and it's a differential equation, right? dy dt, derivative of y with respect to t. Well, what if we solve this differential equation for y, which just means let's separate the variables, and then let's take the integral of both sides. Let's see what happens when we do that. I'll keep that on the screen there. Some of you are still jotting that down. So yeah, our goal here is, this is the differential equation. Let's solve it. Yay, why not? By the way, this way I wrote this, diff EQ, that's usually what, there's a course called differential equations that some of you might take in college. And it's all about differential equations like this, and we usually call it diff EQ. That's like the short name for it. So diff EQ, we get this differential equation, let's solve it. So if we do that, let's rearrange the variables first. Like get all the y's on the left and get all the x's, or not the x's, but the t's, the dt is on the right. Keep in mind, k is a constant. K is a constant. So if I rewrite this, first off, this is going to be 1 over y dy equals k dt. Okay, so that's just rewriting this. Now let's integrate both sides. Integral. This is the easy part, because on the left side, that is natural log of y. I'll just drop the absolute values for now because they're not going to use them later anyhow. And on the right side, remember, k is a constant. So we could have really thought about this. Let's use a little trick here. We could have really thought about this guy as being right here. Ooh, fancy, huh? Paul's smiling. He's like, oh, that was a cool trick, Mr. Defoe. So yeah, we can take that and put it in, and take the k and factor it off. So what is the integral of dt? It's just t. So this is just kt over on this side plus some c. Let's just call it c1 for now, because we're going to make some changes to it later. Okay, so far so good. Now remember what we did in that last example. How do I get rid of the natural log part of y? I need e raised to the natural log of y, but I have to do that on both sides of this equation now. So I'm going to rewrite this here and say, well, this is actually, oops, I almost lost my pen. E ln y equals e to the kt plus c1. So we just raise e to both sides. This is, I guess, the best way to say that. Raise e to both sides in this particular step. But the left-hand side, hopefully we're all pretty comfortable with what that turns into. E to the natural log of y just turns into y. So we've got our y. And now we just got to simplify the right-hand side. Well, let's go back to that trick I had used before, that if I have x to the a plus b, that's same as saying x to the a times x to the b, using this exponent law. So I can rewrite this part here as e to the kt times e to the C1. So that's just applying that exponent law over here. But what would I say we could say that e to the C1 really is? I mean, is it still a constant? Yeah, it's still a constant. So I could really just say, oh, let's just call this C. Combine them together and call it C. So it leaves us with our final equation being y equals, I'm going to bring that C out front, C times e to the kt power. So what we just did here is we derived theorem 5.16. That was the derivation for it. Okay. Yeah, so and what this is saying is, well, let's break down what each of these things mean, the C, the K, and the T. Okay, so first of all, Y is just some quantity. All right, could be money, could be a population growth thing, something like that. So what the C represents, C is just the initial value of Y. So if we were talking about the growth of some money in some account, that'd be like, oh, how much do you put in the account at the beginning? And T is just our time, of course. Let's just write that down. I wasn't going to write that down, but this is our time. And it just depends on the problem, whether it's in days, hours, seconds, minutes, whatever. Okay, could be years. So T is time. K, that's just our proportionality constant. So that didn't change. I mean, K was our proportionality constant when we started with this. It's our proportionality constant still now. That didn't change at all, that variable. So the interesting thing about this, when we're considering, well, what's K mean here? So we get growth if K is greater than 0. If your proportionality constant is greater than 0, our initial value, C, is going to grow. It'll get bigger over time. And we're going to get decay if K is less than 0. All right? If it's negative. So it means just we're like, we're getting population die off, or we're losing money in an account by a certain rate. Because some of you, I think it probably looks familiar to some of you that this is, you've seen a different version of this formula. It looks like this. For like the amount of money you put into an account, or some, well, usually we use principal in the other thing, but usually you've seen it maybe like this. Your total amount of money in some account, if you start off with the principal P, is equal to EKT, where this is like how many years you got something in an account, a bank account, and this would have been like percent interest rate. So you make 10% over time in an account over T amount of years. This would actually calculate for you how much you'd have in that account after T years. And that's something you've probably seen not just in pre-calculus, but maybe you've come across it in maybe some other classes where you're doing some finance type stuff. And that's compounded continuously, if you're wondering about the compounding piece. So all that being said is, well, can we actually like apply this to some sort of problem here? Let's see how much time we got left here. Why is my thing saying that was weird? All right, anyhow. Yeah, we got 13 minutes. All right. So I want to actually apply this to a problem. Okay, let's do a growth problem really quick here. So we'll keep this. This is going to be our key thing that we're going to be using here. This growth formula here, or decay, depending on our situation. So just quick things about possible applications of this. So money is obvious one. Population growth, that's an obvious one. But we will also use this to figure out things like half-life, using half-life and to figure out radioactive decay. So that's another aspect we can use with this. So and some of the problems you'll look at will be that way too. So let's say we've got this example problem here. I want to figure out for some exponential growth. That's what this problem is going to be dealing with, exponential growth. So we're told that y prime, in other words, the derivative of y, dy dx, is proportional to y. So we have this situation. So all I'm doing is saying, all right, the rate of change of y is proportional to y. Okay, now we have a situation where we can now use this formula here, right, that I have highlighted. Okay, so that's all that's telling us. So if I say that is true, now that we can apply that. And we're given this situation, and I guess you could say this too. We're really saying y prime is equal to ky. So just keep that in mind. The situation is when t equals 0, y equals 3, and when t equals 5, y equals 18. So that's the situation here. So think about it like this: those would be 2 points on a graph, but I know it follows exponential growth based on this information right here. So I should be able to fit these things. Well, if I want to find a model for this, I should be able to fit them to that equation, the y equals c times e to the kt. So the first thing I want to do here, first instruction is I want to find the model for f of t. In other words, this function as I want to find a function with regards to time of how this thing is changing. Now keep in mind, I'm really starting with the y prime here. Okay, so we're gonna have to do a little bit of derivation, well, not derivation, but a little bit of integration to figure this out. So keep in mind, this just means, in other words here, y equals c e to the kt. That's really what we're saying here. Okay, and then I also want to find what y is. Find y when t is equal to 10. Okay, because right now I wouldn't know what that is. I was given these bits of information up here right off the bat, but I'm given both bits. So I forgot my end there. So now what happens at 10? Could I make a prediction there based on our formula? So let's go ahead and see if we can figure this out. So part A here, in terms of our work, or our solution to this problem, we start with y equals c e to the kt. So I'm just going to start with that bit of information. Don't change anything there. But here's the simple thing I'm going to do. I'm just going to say, okay, let's take our first point, 0, 3. Let's just plug it in. Let's see what happens when we plug in a t value of 3 and a y value, or sorry, t value of 0 and a y value of 3. So that's a t, that's our y. And just plug them into this. Because what do I really need to do here? If I'm going to come up with an equation, I need to figure out what my c is, and I need to figure out what k is. All right, so there is a way for us to do that. So let's go ahead and plug those in. So we end up with 3 equals c times e to the k times 0 power. Well, k times 0, 0. So what's e to the 0 power? Poof, it's just 1. All that turns into 1, which is a nice way of saying that c is just equal to 3. Okay, so far so good. Now we can now conclude that y equals 3 times e to the kt. All right, so I've taken care of c. Now all I got to figure out is what's my k. All right, y and t, keep in mind those are our variables. We don't need to replace those. I just need to get my k here. But I have another point that I haven't used yet. Got 5 comma 18 up there. So let's go ahead now and let's just plug in 5 comma 18. Kind of do the same thing we're just doing. So 18, let's use red again. 18 equals 3 times e to the k times 5, or 5k. So this is solvable. I can solve this equation. I can divide both sides by 3 and make this equal to 6 equals e to the 5k. Now, how do I get that exponent out of, or how do I get that k out of the exponent? We're just going to take the natural log both sides at this point. Take natural log of both sides, so I get natural log of 6 equals, well, this just turned it into 5k, right? Bring that 5k out front. Natural log of e just turns into 1. And I can divide both sides by 5 So this is a point where you pop this into your calculator. And when you do that, I'll save you the trouble. You get a K value of approximately 0.3584. So that's our K, and it's rounded a little bit. So after all that being said, I now can say my final answer for Y. Now that I know C is 3, and I know my K value is 0.354, I can say this is 3584 T, and that's what we can use now to model this situation. Remember, this was with those growth parameters. I said, well, at 0, it starts at 3, and at 5, it's at 18. So now I can look at a model for this. I could actually punch this into Desmos and see what it looks like. And you see it would be some exponential growth that goes up like this. An interesting little thing before we move on to the last part, finding part B, because that's pretty easy here, just plugging those in. 0, 3. So some of you guys know some things about exponential equations. Because whenever I have generally an exponential equation looks like this. It's like, well, it's some constant times some base raised to the x power if it's just some general thing, or some kx power if you want. So even if there was a k here, whenever you have 0, something, and you plug in 0 for x, well, this whole thing just turns into, well, b to the 0 power or 1. So what do you always end up with? Your constant out front. So that being said, remember our constant in this one turned out to be 3. Well, one of our points that we started off with was 0, 3. So if one of your initial points is 0, something, the comma something part, that's your constant. That's always going to go out front. So we could have saved ourselves a lot of trouble and recognized like, oh, this, doing all this work here, I don't really need to do it. If I'm given 0, 3, that's my constant out front, which is kind of nice to know. It makes this a little bit simpler. I can kind of skip that step in the future. But last thing we needed to do was to, in part B, figure out what happens when t equals 10. Right? I think that's what we had. Right. What's y equal to at that point? So this is just a matter of just plugging this in. You say, all right, y equals 3 times e to the 0.3584 times 10. And you plug that into your calculator and boom, you got your answer. And I'm not, since we're kind of short on time, well, actually, I'm probably not going to do the half-life model. With y'all, I might start it here really quick. But yeah, that you plug that in and you should be able to get your answer for what is the population or whatever the situation is at a time of 10. So keep in mind in this problem, we weren't given any parameters of this. Is this a population growth thing? Is this a money growth thing? What is it? We're not quite sure. So it's just a pretty general problem here. Now, I'll tell you what this is equivalent to. If this was a money problem, and I said, I'm going to invest $3 initially into a bank account, but it's going to grow at a rate of 35.84% per year. That would be the equivalent here of this being a money problem, because this is like your percent growth here. So 35.84% growth would be our situation here. Your money growing, only $3 to start with, but that would be the situation. So after 10 years, whatever answer we get for this would be equivalent to that. Now, it's not a very good example of a money problem, but that's just kind of putting it in context a little bit. Let's go into an example with decay. We'll focus on a half-life model, but we can have all sorts of different decay. So, we got growth. That's where, obviously things are increasing. So we have exponential growth. You've heard it before, but we can have exponential decay as well. So a good example of that is half-life model. And there's a bunch of problems that deal with that in here. Specifically, 33 through 35, you'll have to do some half-life stuff with radium-226 isotope. But we're going to focus on this half-life model. So what do we do with the half-life model? And for our particular problem here, and I'll give you a chance to jot some of this down, we're going to deal with carbon-14, so which we use in dating things sometimes, whether you feel like that's accurate or not. There are some questions about that when you do really far back dates using carbon-14, but it is pretty accurate for relatively recent times using carbon-14 dating. So anyhow, it has a half-life of 5,730 years. So just a reminder what that means, if you forget what half-life means, it means we had a certain amount of carbon-14 isotope 5,730 years ago. Today, there would be half of that amount left. Okay, so if we knew what the original amount was, we said, hey, there's 100 grams back then, now we have 50, that means that 100-gram sample started 5,730 years ago. And if we did half of a half again, in other words, if we had a 100-gram sample and now we're down to 25, that means we've halved it twice, which means we'd now be at 2 times 5,730 years, and so on. Excuse me. So what we're going to do is we're going to try to come up with a model for the amount of a sample left after t years. Okay, so we're doing this as a function of time, obviously, which most of these are. Okay, a couple things though. What's this amount of a sample mean? Because I didn't actually give you an amount. I didn't say how much would be left after t years for 100 grams or 50 grams or 100 kilograms or whatever. So the amount of a sample, remember the context of this is when we're going to use this formula, y equals c times e to the kt. This is really what we're going to try to figure out here. We're really talking about c, right? So the amount of a sample, this is c. That's what we start with, right? We start with c, and we end up with something less than c if we're talking about decay. So I'm just going to keep it c. I'm not going to change it. We'll just say, all right, amount of sample is c. And we got our t for t years. So really what we just have to do is figure out, well, what is k? How do we find k? And how do we find k without knowing what our initial thing was? You know, at t equals 0, what do we do? Well, we're just looking at it like this. We know that at t equals 0, c equals, well, c. That's what we're trying to do here, okay? That's pretty much it. But then we're like, well, you know, I'm putting in the context of these problems up here, where we, like this one here, we knew what happened initially, t equals 0, and then some time down the road. After 5 years, it was 18. So how do we get the second one here? Well, that's pretty easy. We know the half-life, right? We know at t, and well, I guess put it this way. Actually, I should have said this here. At t equals 0, y equals c. At t equals 5,730 years, what's y going to be equal to? How can we write that? Any idea?
Half of c.
Half of c. Yeah, we just write it in terms of c. Half-life. So if I started with 100, if c had been 100, then this would be 50. If c had been c, now it's half of c. So it's not super complicated. It's kind of stepping back and saying like, wait, this is actually that easy. Just say it's half of it. Okay, half-life, half left. Okay, so we can actually go through the same process here and plug these numbers in and go through this. Remember, when we plug in t equals 0, that helps us to figure out what c is. But we kind of already know what c is at t equals 0. We don't have to do anything with this. I mean, I'll show you how it works. So what happens when we say, all right, t equals 0 and y equals c? If we plug those in, we say c equals c times e to the k times 0. That turns into 1. Well, c equals c, duh, right? So we don't even have to do this step. We already know that c is c. We're not going to change that at all. So really, we can just jump to using this information. So for future purposes, when you go to do your decay problems for like 33 through 35 for radium, don't worry about this first step, okay? Don't need to do it. We already know what that c equals c. We'll jump right to saying, okay, what happens now when I have a c value or y value that is 1/2 c? So I'm just going to plug in 1/2 c for y up here, and then kind of go from there. So 1/2 c equals c times e to the k, and now this is going to be 5,730. So somebody tell me what happens to the C's?
Cancel.
Cancel. Yeah, poof, no more C's. Divide both sides by C. Remember, this is C times this here, so I can multiply that. I don't want to make it look like a subtraction. So yeah, I basically can cancel them out from both sides. So this is really saying, well, 1/2 equals E, and I'll write this with the 5,730 first. That many K's. So how do I solve for K? Do what to both sides? Natural log. I heard Anthony mouth. Yes, I heard him, saw him mouth. So yeah, I can just go ahead and take the natural log of both sides, or technically you can also apply the definition of a logarithm. But anyhow, natural log of both sides here, natural log of 1/2 equals natural log of e to the 5,730k, which of course, what's the whole right side turn into? Just 5,730k. That's that one property. Take natural log of e just turns into 1. You bring this out front, and that's all you have left. So that's just equals the natural log of 1/2. Divide both sides by 5,730, and we've got what k equals. So bust out your calculator really quick. Do a little natural log of 0.5 ln 0.5 divided by 5,730. Make sure you put the parenthesis around the natural log of 0.5. And we get a really small number, a very small number for our k factor. It is negative, though. Take a natural log of 1/2, that's where the negative comes from. With the negative, it's like sometimes 10 to the -4th, right? That's what that little e means if you're doing this on your calculator. So it just means we're moving the decimal place over back to the left 4 decimal places. So this would be 0.000, and then comes in our 1, 2, let's do 121. It would round off to about that. It's 12096, but yeah, I'd want round to 121, 1210 if you wanted. So that's our k. So what is our model? Well, let's just fill in the blanks, right? Our final model here is y equals c, still dealing with the c here, times e to the k, which is now 0.000121 t. There's our model. And you can test this fairly easily, actually, because you would expect if you do e and then use a time of 5,730, if you plug that in, you expect to get a 1/2 out of it, right? Because it'd be, it'd be the half-life, 5,730. Plug that into t, you should have this whole part here turn into 1/2 because you'd expect to have 1/2 of your sample left. So an interesting little thing to note here, though. Okay, because wouldn't this be the same process for any radioactive isotope if with a known half-life? Because on this one, the half-life, our known half-life was 5,730. But let's say we were doing this for plutonium, plutonium-239. I'm just looking at the book here. It has a half-life of 24,360. 24,360 years, half-life for plutonium. Okay, well, can I just replace this with 24,360, and then I could figure out an equation that would give us this model for plutonium? Yeah. In fact, all the way down through here, notice at this step right here, we have k equals what? Natural log of 1/2 or 0.5 divided by, what's this quantity represent in general? 5,730. That's just our, anybody? Tell me something.
Half-life.
Half-life. So this is actually a formula you could use to find k. Instead of going through all this rigmarole, right? I mean, you could do that, but we could solve this once for all time and just say, oh, this is how we can find this half-life. So yeah, if you plugged in right here, this 24,360. Well, there's your K for that formula. And it's going to obviously give us a different number there, but that's one way we can do it. So anyhow, the point is now I can use this formula if we wanted to use this in the context of one of these problems. I said, oh, I've got some carbon-14. I'm starting off with a sample of, I don't know, 300 kilograms. How much is going to be left after, I don't know, 76 years? And I'm not going to go through the process for that one because that's pretty simple. This is our C. This is our T. Obviously, it's got a T equals. We plug those into our formula up there, and you've got yourself how much you got left after 76 years. Where this gets a little bit more interesting is if I change this up and say, well, I've got a carbon-14 sample, and I have, let's say, let's do it this way. Yeah, I have 50 grams left. 50 grams left of that. And it's been 1,000 years. What did I start with? What did I start with? That's a little bit different type of problem, right? So I have this much. Whoops, I didn't want to cross that out. I've got this much left. So 50 grams left. So that's not my C anymore. What would that be? What would that represent in this context? Going up to this formula up here. 50 grams would go where? Y, C, E, T?
Y.
Yeah, it'd be our Y. And what did I start with? What's that represent? So this is our Y. This is our Y. What's
C.
yeah, this is our C. And of course, 100 years, that's our T. So if you plug that into that formula up there, it's a little bit different. We'd say, well, I have 50 grams left. I'm trying to figure out C amount with E raised to the, what was it again? Negative 0.000121 times 1,000. And of course, you just have to solve this equation for C. This is actually a pretty easy one to do because you just divide you divide each side by this quantity here. In other words, 50 divided by that, and you get your amount you had started with. Which, well, let's just do that really quick, huh? Let's try it. Why not? 50 divided by second e to the x raised to the negative 0.000121 times 1,000 power, and I get a C value. Let's not use that. A C value of, what'd you get? What? And remember, this is how much we would have started with. So it makes sense. If it's bigger, it should be bigger, right? You'd expect it to be a larger quantity than what you started with. So if you get a smaller quantity, you did something wrong. Okay. I mean, you could do a little bit of quick math in your head too and be like, well, if the half-life is 1,000 years, or sorry, 5,730 years, we've only gone 1,000. It shouldn't be very much, what I currently have shouldn't be very much smaller than what I originally started with. I got 56 let's just say 4 grams would have been what you'd initially started with. Something around there, okay? So you kind of get the idea and approach on these. So I guess the only other thing we could do here is involve time in some way or another. Which if I had a situation that says, hey, I've got carbon-14 or whatever, and I have a sample now that is 50 grams, and it started off as 121 grams. What's T equal? Okay, so I mean, that doesn't change things much. The now would be our, well, is that C or is that Y? What I have now? Tell me.
That'd be y.
That'd be y, which means this has to be our c. Was as in what did we start with in the past? This is our past, what we started with. Now is the present. Or do we live in the future? I don't know. So yeah, you plug those into this formula here, your y and your c, and you'd solve for t. So in that particular case, there's going to be some point along the line where you would need to take the natural log of both sides to get that t out of the natural log position. So I think you get the idea, hopefully, at this point.